Hello, my name is Andrew Jensen. I'm a graduate student at Northeastern University working towards a master's degree in computer science. My topic for this presentation is AlexNet. AlexNet is a large, deep convolutional neural network developed for image classification, and it won the ImageNet competition in 2012. The network, which has 60 million parameters and 655,000 neurons, consists of 5 convolutional layers, some followed by max pooling, 3 fully connected layers, and a final softmax layer that outputs probabilities across 1,000 classes. Back then, this was considered big for a CNN. The AlexNet paper was published in 2012 and is officially titled ImageNet Classification with Deep Convolutional Neural Networks. I'd recommend you'd read this at least once because it's a very influential paper. As of 2025, it's been cited in over 184,000 other academic papers according to Google Scholar. AlexNet was developed by 2 PhD students, Alex and Ilya, and their PhD advisor, Jeffrey Hinton, at the University of Toronto. AlexNet was named after the lead author. Ilya went on to co-found OpenAI, and Jeffrey is often called the godfather of AI. Before AlexNet, a few things were still coming together. Large labeled data sets like ImageNet had just been introduced to researchers. CNNs existed, but hadn't yet proven they could outperform hand-designed features at scale. And GPUs existed too, but training a deep CNN on GPUs at this scale hadn't been done before. AlexNet was really the first time all of these pieces came together at once. The dataset behind AlexNet's success is ImageNet, a large-scale database with over 15 million labeled images. Starting in 2010, it ran an annual competition where teams competed to build the best image classification model using a subset with 1,000 categories. The task: given an image, produce your top 5 prediction for its category. If the correct label is anywhere in those top 5, your prediction is counted correct. That's what top 5 error rate means, and it's how teams got ranked. As mentioned earlier, AlexNet has 8 learned layers, and I'll walk through each layer in detail shortly. A couple of key features made this architecture perform well. It was one of the first major uses of the ReLU activation function, which trains several times faster than the previously common activation functions sigmoid or tan. It was also trained across 2 GPUs, since the full network was not able to fit in a single GPU's memory at the time. To help prevent overfitting, AlexNet used 2 main techniques. First, data augmentation, cropping and flipping of images, and altering the intensities of the RGB channels. This artificially increased the training set without needing any new images. Second, dropout, a technique where they randomly zero out 50% of neurons during training, so the network can't rely too heavily on any one neuron and is forced to learn more generalizable features. Here's the architecture as presented in their 2012 paper. The first 7 layers were split across 2 GPUs, and they merged back together only at the final layer. I wanted to show you this diagram directly from the paper before I walk you through the architecture using a simpler version. And here is the simpler version, shown as one continuous chain instead of split across 2 GPUs. This is the version I'll use in the next slides. Also, if interested, I included the formula used to calculate the output size after each convolutional layer, since that's how we'll track the dimensions layer by layer. Layer 1's input is a 27 by 27 RGB image. Quick note, the paper's text actually says 224 by 224, but this is a known inconsistency in the original paper, and the math only produces the stated 55 by 55 output with 27 by 27. Conv1 applies 96 kernels of size 11 by 11 by 3 with a stride of 4 and no padding. That gives us an output of 55 by 55 by 96. That's followed by ReLU, then local response normalization, which encourages competition between nearby kernels. Finally, Pool 1 uses overlapping pooling, a 3x3 kernel with stride 2, bringing the output down to 27 by 27 by 96. Layer 2 has the same steps as Layer 1, but the numbers are different. Conv 2 uses 256 kernels of size 5 by 5 by 96, stride 1, padding 2, giving an output of 27 by 27 by 256. Then ReLU, local response normalization, and pool 2, the same overlapping pooling as before, bringing it down to 13 by 13 by 256. Layer 3 takes the 13 by 13 by 256 output from Layer 2. Conv 3 applies 384 kernels by size 3 by 3 by 256, stride 1, padding 1, giving an output of 13 by 13 by 384. This layer just has ReLU applied, no normalization and no pooling here. Layer 4 is the same as Layer 3, except the input and kernel depths are different. Same stride, padding, and output size, just a separate set of learned weights. For Layer 5, Conv 5 uses 256 kernels of size 3 by 3 by 384, stride 1, padding 1, giving an output of 13 by 13 by 256. Then ReLU and pool 3, the same overlapping pooling as before, bringing it down to 6 by 6 by 256. Finally, we flatten that into a vector of 9,216 values, so it can connect into the next fully connected layer. Layer 6 takes that flattened vector of 9,216 values as input. FC1 is fully connected, outputting 4,096 values. ReLU is applied here, and during training, dropout is applied too. Layer 7 takes the 4,096 values from the previous layer as input. FC2 is fully connected, again outputting 4,096 values. Just like before, ReLU and dropout are applied. Layer 8 takes the 4,096 values from the previous layer as input. FC3 is fully connected, outputting 1,000 values, one for each class. Softmax is applied here, converting those values into probabilities. Whichever class has the highest probability is the network's final prediction. AlexNet trained on the 1.2 million images from the ImageNet training set, plus the images they added from data augmentation. It used stochastic gradient descent with an initial learning rate of 0.01, momentum of 0.9, and a batch size of 128. They also used a small amount of weight decay, 0.0005, which they found was important for the model to learn. Dropout was set to 0.5. They trained for 90 epochs using 2 GPUs. In total, training took 5 to 6 days. Now let's look at the results. Before AlexNet, prior ImageNet competition winners had top 5 error rates of 28.3% and 25.8%. In 2012, AlexNet achieved a top 5 error rate of 16.4%, using only the officially supplied training data, and with extra training data added, the error rate dropped to 15.3%. In the 2012 competition, the authors of AlexNet formed the team called Supervision, and they achieved a top 5 error rate of 15.3% to win the contest, approximately 10% better than the next team. AlexNet was the first CNN in history to win this competition, and unlike the other teams which relied on handcrafted features such as SIFT and Fisher vectors, AlexNet learned its own features directly from the data. The authors closed their 2012 paper with 3 ideas for future work. First, use unsupervised pre-training, since they believe it'll help improve their model's accuracy. Second, build bigger, deeper networks, because their results kept improving as they made the network larger. And third, extend this to video, since motion adds information a still image can't. Looking back, that's essentially what happened. AlexNet inspired later architectures like VGG, GoogleNet, and ResNet, and helped establish deep learning as the dominant approach in AI and computer vision. Here are the sources I used for this presentation: the AlexNet paper itself, along with the diagrams and charts that I used throughout. This concludes my presentation. If you have any questions, feel free to contact me via email. Thank you.